Hi everybody, my name is Fraser Cain. I'm the publisher of Universe Today, and this is your weekly space hangout for June 28th, 2012. This week, we're going to be talking about a terrifying gas cloud that is headed towards the center of the galaxy. More news on exoplanets, sniffing for life on Mars, and what it's going to be like to land on Mars. Now, joining me this week are three of my favorite space journalists. We've got Emily Lakdawalla from the Planetary Society. We've got Dr. Ian O'Neill from Discovery Space, and Jason Major from Universe Today and lightinthedark.com. There we go.
He's omnipotent.
He's everywhere. When I'm about to introduce Jason, I always forget because he's kind of everywhere. National Geographic, Discovery Space, yeah. Hardest working man in space journalism. So, and for anyone who hasn't seen it, I'm going to do just a tiny little bit of log rolling here, which is there was a really cool video that was a documentary that was produced by Google and released and announced yesterday during the keynote address at the Google I/O conference down in San Francisco. And it highlights the virtual star party that we do on Google+. So it's like a 3-minute long documentary talking about all of the telescopes and astronomers and how we bring this all together and broadcast it on Google+. And so if you haven't seen it, you can see it in my stream. We've got a post over on Universe Today, and it's pretty great, and I'm really proud of it. And I'm really proud as well of all of the astronomers that have been joining us. So definitely check it out. Yeah, it was really cool. It was really cool. All right, well, let's get rolling first. Jason, I'm going to start with you, and we're going to talk about a terrifying gas cloud that is on its way to the center of the galaxy. And when this happens, what's going to happen?
When this happens, well, that's the trick. That's what we're trying to find out. You know, what's going to happen when this gas cloud actually reaches the monster in the middle of the Milky Way. In the middle of the Milky Way, our galaxy, and a lot of galaxies actually, they're finding there's a supermassive black hole. I mean, there's black holes, and then there's supermassive black holes. This one here, that's at the center of our galaxy, is approximately the mass of 4 million suns. So you take all of that mass and you smash it down into an area. I'm not quite sure what the radius of this thing is, but it may be around something that would fit within the orbit of the planet Mercury. So you have all of that mass smashed down in there, and you're going to have a really, really massive object and basically an enormously powerful black hole. So the problem with black holes is you can't really see them because they don't, the jury's out on this, but they don't emit radiation that is visible outside of what gets chucked out, because when it comes down to it, they're kind of sloppy eaters. So astronomers using the VLT telescope over at ESO's Paranal Observatory have spotted a giant cloud of charged gas particles heading towards this very same black hole. And it's not, you say a cloud and you think of something that's up in the sky, but this is actually an enormously massive cloud. It's somewhere along the lines of 3 times the mass of Earth. So it's a good-sized cloud of material. It's hotter than the surrounding gas that's already around that black hole, and it's moving at something like 8 million kilometers an hour, heading straight towards this thing. And they've been watching it for a few years. It's been speeding up. And at some point this month, it's going to be around, I think the estimate was something like 36 light hours from the supermassive black hole, which has the name Sagittarius A star. So that's what they call this really, really dense object. What's going to happen when it reaches there? They're not quite sure, and that's why this is so exciting. We're going to actually be able to watch a black hole feed, and it's going to, I mean, estimates say that it's going to be pulled into a long strand in a process called spaghettification. In doing so, this gas cloud is going to be ripped to shreds. It's already started to break up a little bit. And in doing so, getting ripped apart, it's going to be throwing out X-rays and all sorts of other cool radiation that they can keep an eye on. So that's the process. And here in the picture that Fraser's got put up, or Emily has put up here, you can see the movement of the gas cloud between 2002 and 2011. So it's just kind of, it's poking along over there, but in reality, it's going really, really fast. So,
yeah, and this is the situation, right, where these events they put out so much energy that you can even detect fairly minor amounts of material being consumed by these supermassive black holes, and it's the bursts of gamma radiation that come in the surrounding area around this black hole, and so I guess being able to, but I think the more incredible science here is the fact that they're able to spot this gas cloud on its way to reaching the supermassive black hole, and then they're going to be able to just really be able to tighten this up and see, okay, if this amount of material makes its way into a black hole, this is the amount of energy that we see released, this is the way it gets spread out, this is the way it gets destroyed and shredded. So this is I think one of the first times they've been able to really, they haven't any kind of knowledge in advance, but I mean, kudos to the science team to be able to detect this gas cloud, 30,000 light years away, this close to the supermassive black hole. It's an unbelievable scientific discovery.
Previously, the only thing that they've been able to observe with Sagittarius A star is the motion of big stars that go around it, and that's really how they were able to kind of pinpoint where it is. Now they're going to be seeing matter actually falling into the accretion disk of a black hole, and what happens when it reaches that point of no return, where stuff really starts to break apart and things get wild.
And I know there's some recent research as well that is starting to overturn some of the thinking that supermassive black holes are, when we see these actively feeding, these quasars, right, these actively feeding supermassive black holes, that they've been doing that for a long time, and now it seems more that they've been doing it a little more intermittently, that it's more in bursts of feeding. They go active and then quiet again and active again, as opposed to necessarily active for long periods of time. So I think with this, we'll really get a chance to see this burst in action. When's this expected to actually happen?
Well, it's like I said,
December 21st, perhaps 2012.
Yeah. Well, the feeding process is estimated to it's going to take a while, and it may actually take place over the course of 10 years. So it's something that they'll be able to. It's not like a blink and you'll miss it type thing. They'll be able to really see what's happening here for a while.
But like, when do they think it might start?
I'm not exactly sure when it's actually going to do the falling in part, and I think that's what they're trying to find out. They know, like I said, this month it's 36 light hours away from the black hole, and that's close in astronomical terms, although it's still twice as far as where Voyager 1 is from us. So it's a long way away in human terms, but it's still really close in astronomical terms.
But within the next few decades it'll happen.
Oh yeah, I mean this is by next year.
Oh, by next year, okay, yeah.
By 2013, they think this process will begin, and then they'll have another 10 years to watch.
That's all I wanted to hear. Next year,
or the end of this year.
Or the end of this year. That's great. So that's really
around December 21st. No, never mind.
Yeah, because you mentioned that it's going to produce like X-rays and possibly gamma rays. I mean, I'm sure people are thinking, that's kind of scary. I mean, is there a threat to us? I mean, say if our black hole suddenly gets all hungry and turns into a quasar and suddenly starts generating all this radiation. I mean, are we far enough away? That's what I want to know.
I'm going to use my non-scientific background and say, yes, we are very safe from a distance of 25,000 light years away.
That's all I need.
Don't cancel your plans. Don't max out your credit cards. Unless you really want.
I mean, seriously, the only event that could hurt us from that far away would be a gamma ray burst. And it happened to be aiming directly at us. Right down the channel. And those don't happen very often, and there's likely no stars. So in case anyone doesn't realize the level of sarcasm that's going on here, Dr. Ian O'Neill, there is absolutely no problem, no risk, no chance. All we'll get is maybe some slight detection of some gamma rays and some X-rays. Are we clear?
Very cool. And also because they're trying to actually image a black hole. This is one area of study that I've found captivating. Is astronomers want to hook up many radio antennae across the world, interferometer, and they want to aim it at a Sagittarius A star, and they want to actually start being able to image the event horizon surrounding the black hole. I mean, imagine being able to see the disk of the sphere of influence of a black hole. That'd be phenomenal. Well, if they could do it in time for the speeding, that'd be even better.
This is the big question, right? Which is, how big is the event horizon? How big is the accretion disk? How big is the gap around these supermassive black holes? It's been thought that the event horizon around a supermassive black hole could be the size of the solar system. That you could drift into essentially the point of no return of a supermassive black hole, be traveling for the better part of a couple of weeks, but not even realize and not really feel huge tidal forces, and yet you're never coming back out. You and the light are never coming back out. So anyway, let's move on. But it is really exciting. I think that's great, Jason. All right. Well, so Ian, you've got a couple of stories you wanted to talk about. Let's first talk about sniffing for gas for farts on Mars.
Yeah, I resisted putting that in the title.
I can't help it.
Damn it. Yeah, so smelly Martians.
Smelly Martians, yeah.
Now this it's a rather elegant idea coming from scientists from the University of Canterbury in New Zealand, and they've been working on a means to perhaps detect microbial life on Mars. Now, we're sending robots to Mars. We're trying to do remote sensing. We're trying to find any hints that there may be or may have been life on Mars, or at least what we're trying to do presently is trying to find the components of life. So perhaps what gave Mars the ability to produce life, perhaps in the ancient past. But these scientists, they came from the University of Canterbury. They came up with a rather elegant solution to trying to find alien life on Mars. Now, they were studying, I think it was actually a separate geological study, into the process of, let me get this right, olivine hydrolysis. Hydrolysis? Yeah, hydrolysis, or serpentinization.
Serpentinization.
If only we had a geologist here.
Damn it. Okay, over to Emily.
I could chat a bit about serpentinization if you want me to.
Just the fact that you can say it very quickly without sort of having to read it off a screen, I think is fantastic.
Yeah, I'm squinting to even
We'll definitely have to go into more detail in a second. We'll let Ian sort of...
I'll tell you what, just tell me when I get it wrong. just cut in there, say
yeah.
You're wrong.
Yeah, thank you. Stick with the sun. Yeah, so they were doing some really they're doing experiments on this really weird rock theory thing that I can't even describe. But they were detecting the emission of methane and hydrogen from the process, and basically the process is the interaction of water with olivine, which is a rock mineral. And so basically by looking at this process and measuring the amount of gas given off, they were able to measure a set ratio of the amount of methane and the amount of hydrogen produced. And for a non-biological system, so basically with no microbes involved, they worked out that there is a very set ratio of the methane to, or hydrogen to methane. Now, they thought, oh, okay, that's kind of interesting. Let's now take this to the wild. Let's take this into the field, and let's look at, say, a hydrothermal vent. What's the ratio of methane versus hydrogen? And they actually found, because there are microbes present, they're producing methane because they're metabolizing minerals within the rock. And so their waste product is methane. And so that's quite a good tracer to find out if there's microbial life present in a sample. And so they took the concept and thought, okay, well, if we can detect this ratio difference, this slightly higher level of methane being produced by the presence of microbial life, how about we just send a sniffing robot to Mars and sit it near an ancient hydrothermal vent, because we know that Mars once had geological activity and there's some low-level stuff now, but ultimately if we stick it near a hydrothermal vent, let it sniff the air, see if that ratio is the same as what we'd expect in a non-biological environment or a biological environment and just see if the ratio is different. And their hypothesis is if there is or was life on Mars, the methane produced by these microbes deep within the rocks of just below the surface, the leakage of the methane that they produce through their metabolism, they would have, that could possibly be detected. Now, I don't know what kind of shelf life, I mean, because I know that if methane is put into the atmosphere on Mars, it gets broken down very, very quickly by ultraviolet light, which is kind of exciting because there's been other studies that shows that there's a lot of methane, well, there's certainly a detectable amount of methane in the Martian atmosphere, which has led to the debate of whether it's produced by geological processes or by microbial processes. So these guys in Canterbury, they're putting together a means to differentiate between the two. And if they can measure this difference in ratios, perhaps they can detect the presence of life. And I just find that really kind of cool.
Yeah, and then this is one of those situations where I think the evidence is pretty compelling. I mean, they've detected possibly trace levels of methane in the atmosphere around Mars, and this is actually, the various space agencies have actually put together ideas for missions that will go back and try to detect these trace elements or these trace amounts of methane from space. And this, you can use various, spectroscopic analysis of the atmosphere to try and detect the methane and to detect the various processes going on. And especially if you can create a spacecraft that's specifically designed to do this. I mean, they just used Mars Express and kind of pushed it to its limits, but to actually create a spacecraft. So this idea of putting a lander down right next to a vent and seeing if you can detect that's taking it to the next level. Does Curiosity have any ability to suss out these gases in the atmosphere?
Oh my, yes. So that's what sample analysis at Mars, the SAM instrument. It's one of the gigantic laboratory analysis instruments inside the body of Curiosity. It's all about carbon and what forms it's in, and even isotopic ratios. So that's one of the big goals of that particular instrument, is to try to understand this question. And then there's also the MAVEN mission to Mars, and looking at methane in the atmosphere is one of the goals of the MAVEN mission. At the same time, I have heard other scientists kind of doubting these methane results, because after all, they're done with ground-based surveys, which have to look through methane in Earth's atmosphere, so they have to correct for that. And if what you're detecting is smaller than the corrections that you're making, then you have to take your detections with a grain of salt.
Do you think the MAVEN mission would definitively just figure it out once and for all?
Nothing is ever figured out definitively once and for all. I don't actually know. I would have to read up a little bit on the science goals and the instruments on MAVEN to answer that question.
So
now, Emily, on Gale Crater, are there any proposed hydrothermal vents in the region of where Curiosity will be landing?
Not specifically that I'm aware of, but there's such a diversity of rock types, and we didn't understand that home plate was a zone of hydrothermal alteration until we really got right on top of it. So I think that Gale Crater is so deep, and we're going to be digging right at its roots, so I would be actually shocked if we didn't see hydrothermal alteration, evidence for it in the past. As far as present goes, I don't know, but I'm sure we'll find evidence for past hydrothermal activity.
But even if life is found, microbial life is discovered on Mars, perhaps in those deep vents, etc., that still doesn't provide, I think, that holy grail of definitive evidence of that life is common in the universe, because there's a possible connection between a source between Earth and Mars that
right.
Possibly microbial.
You'd have to be able to differentiate. Although, if it looks somewhat similar, but yet very dissimilar, like for instance, let's say it's based on RNA, but the genetic structure is really super different, that would be good evidence for the transpermia hypothesis. And if transpermia works, then that also kind of raises hope for life elsewhere in the solar system, just because it's easier to move it around.
Yeah.
Universe, I don't know. But
right, but that's the whole point, that it doesn't necessarily say whether or not life is common around other solar systems, only that life seems to be able to move quite a bit within our own solar system.
Yeah, statistics of small numbers are always a real problem.
Yeah, and then of course there's still this, even if, there's another theory as well that perhaps we're leaving a trail of organic material behind the solar system as it moves around the galaxy. So again, you could, because there's such a great time frame, you could still have life traveling from world to world, even within the whole Milky Way. So I think, to actually detect life is a fantastic step to be able to study and actually get to the point you could do some kind of genetic study on it would be amazing, and perhaps we could trace back the tree of life. But at the same time, I wonder if you can detect in the chemicals some completely alien process that you could you tell that right from the methane and say, okay, in fact, the output chemicals here are just not possible to be created on Earth. So there must be some different life form that
what about
in a
Titan?
different way.
What about Titan? A lot of methane there.
Mm-hmm. Yeah. So anyway, I think this is all really interesting. We're moving into hyper speculation mode. So
this is probably the point in the conversation where I should mention that Curiosity is not intended to look for life on Mars. It is looking for past habitable environments on Mars. So.
And the Mars rovers were only designed to last for 3 months. So. So anyway, but let's talk about Curiosity.
That's different.
I know. No, but come on, Emily. I mean, NASA and ESA do a fantastic job of taking and pushing every piece of hardware and software they have at their disposal way beyond its intended purpose.
One of the distinctions, though, that they're making there, one reason that this is important is because Viking, those landers were explicitly sent to Mars to search for evidence of life, and they failed to find. I mean, there's some people who say yes, they did find it, but most people think they certainly failed to find definitive evidence of life on Mars. And I've talked to Matt Gullenbeck about this, and he's like, it was basically NASA swung for the fences and they struck out. And so if we say that Curiosity is being sent to Mars to detect life and then they don't, then everybody will say, well, that was $2.5 billion wasted. And that's not the point. John Grotzinger, who's the head of the mission, the science team on the mission, points out that finding evidence for ancient life on Earth is actually insanely difficult. Just finding one tiny bacterium in a 3.4 billion-year-old rock is a PhD right there. If you do it, you're set. And so even if fossils exist in the rocks that Curiosity is going to be looking at, the odds of finding one are really slim. Because it's not like Curiosity can walk all over the place and turn over all the rocks the way an Earth geologist does. So it's really important, I think, for us to emphasize that finding life is not the goal, because chances are, even if it's there, it wouldn't see it. It's not designed to do that.
I feel like my expectations have been well and properly managed, but I am still...
You've been paying attention.
I am... no, you know what? Yeah, I mean, I just see the story always is, we report on this, which is, oh, hey, what a surprise, the controllers of the Mars Express or whatever have figured out a way to make that spacecraft search for methane in the atmosphere of Mars, that it wasn't what they expected. Or there was even, there was one Mars orbiter where they figured out a way to tilt the spacecraft and capture an image over a longer period of the orbit, captured at an angle and then directly over, and then as it was trailing away, and double the resolution of the image. That once you have hardware and software on the ground, actually on site, the ingenuity of the engineers takes over, and they're able to find things that they never expected. So I agree that is not the intention of Curiosity, but at the same time, I think that people should be watching carefully, and I always like to bet on the ingenuity of engineers to come up with clever solutions.
Well, while that's true, I think if they were looking for fossils, they would have sent a different set of instruments.
I agree. And I think that they're going to do a lot with what they've got. So that's it.
Thank you, Senator Cain.
No, I understand. Those political ramifications and all that. I totally understand that you can't just go and send that the Viking mission was a real lesson learned by everybody on the process. That it did a lot of things, but it also failed to find the one thing it was looking for, that incremental steps in everything is the way to go. So anyway, I'll get off my soapbox. But Emily, let's talk about Curiosity some more, because Curiosity is now only a couple of months away from reaching Mars, and the landing is going to be really exciting.
Yeah, it will be, and there's a lot of, I think, misunderstanding about how this works, and people kind of freak out because of that, because they're mostly concerned about one particular step. I've got a photo of it right here that I'm going to share. This is the step they're scared of. This is called sky crane. This is where a rocket jetpack attached to the rover actually lowers the rover on 3 rather thin-looking nylon cables. And everybody looks at this and says, those guys are freaking out of their minds. Why are they doing this? And why change things from the way that it's worked in the past? And there's several reasons to change things. The main ones that they were trying to do with Curiosity, there's actually 3 reasons they had to change things from the way that they did in the past. One is because the weight of the rover is much, much heavier than anything previously landed on Mars, except for the Vikings. It's actually somewhat similar to the Vikings, except that this has got to be a mobile platform where the Vikings were standing still. So you have to somehow get this incredibly heavy thing on the ground with wheels on the ground without having to land much of any extra equipment. If you recall, the Mars exploration rovers were packaged inside this kind of origami tetrahedron that unfolded, had airbags all around it, and the rovers rolled off. The actual mass of the rover was really, really tiny compared to all the stuff that actually landed on Mars. When you move up to something bigger, you can't scale up the airbags. So you had to be able to land all of that mass in a different way. The second thing was that they wanted to make the landing ellipse smaller. Landing ellipse is the sort of area where you have a 99.9% confidence that your landing system is going to put the spacecraft down inside that area. For all previous missions, the landing ellipse has been really, really long and skinny. The spacecraft comes in along a certain trajectory, and it's aimed at a certain point. But depending on how puffy or non-puffy Mars's atmosphere is on that particular day, it can either go way short or go way long inside that landing ellipse. And so, so what they needed to shrink that landing ellipse, because that whole landing ellipse needs to be safe for the rover to land, which means it's got to be relatively rock-free, have low slopes, no major hills or craters poking down into it. And in the past, that has really sharply limited where spacecraft can be put. For Curiosity, they wanted to make it really small, only about 20 or 25 kilometers across. The third thing is that they wanted to be able to land the package at much higher elevations than in the past. In the past, you have to use an awful lot of Mars's atmosphere in order to slow your spacecraft down, and that's precluded landing at any elevation above, like, I forget what it is, it's like 1 or 2 kilometers below the mean elevation of Mars. And that also has sharply limited where spacecraft could land in the past. So that was the 3 things: heavy weight, smaller landing ellipse, and higher elevation. The ironic thing is that, or one ironic thing, is that they managed to accomplish a landing system that can do this, but they didn't wind up needing the high elevation part of it because they picked a landing site that is at one of the lowest spots on Mars. So that's actually kind of wasted capability for the landing system.
But isn't part of it as well that they don't want to kick up a lot of dust when the rover gets placed down that could ruin its equipment? And so
yeah, well, that's one of the things that that Sky Crane is for. Yes.
Sorry, Jason, can you actually play that animation? Well, is that going to work?
I don't know. I'll give it a shot.
Yeah.
Let's see what happens.
While Emily's talking, we can see some of the pieces of the animation. Yeah, try playing it. See what happens.
Sky Crane that will be lowering MSL down.
Yeah. So just play it, and then while Emily is talking, hopefully this will.
Let's start from a little bit earlier, because most of the rest of it, actually the real innovation, there's 2 major innovations. Sky Crane is one of them, but the other one is what's called guided entry. So if we can go back to the part where it's just beginning to approach Mars. Even before that.
Oh, you got the little puffs of of propellant coming out as it's
right. So I don't know if this
is working great. I think. Yeah.
Yeah.
People are watching this can tell me if it's not working, but I think the animation is coming through.
Okay, so what you're seeing right now, if you're seeing the animation, is you see all those little puffs of rockets behind the spacecraft. It is actually steering itself as it falls through the atmosphere. This is absolutely brand new. No other mission to Mars has ever done this before. Previous ones have fallen ballistically, just like cannonballs. They couldn't control where once they got to the top of Mars's atmosphere, they couldn't control where they were going. This one is actually flying. It's going to be the first aircraft on Mars. It could even fly uphill, or up in elevation in order to fly out all those atmospheric variations that we're talking about. So here's the parachute. This is very similar to all past missions. It's a larger parachute than in the past, but it's basically the same as a Viking parachute otherwise. When they drop the heat shield, they expose the rover as well as a radar ground detection system that helps it understand where the ground is. That's the scariest point in the whole process for me, is when it drops out of the back shell. It actually has to free fall for 1 complete second before they turn on the engines so that it doesn't re-encounter the back shell. So it actually accelerates quite a bit during that one little step. So now they're descending under 8 rockets the same way that other rocket-assisted spacecraft have descended in before. And Fraser, you're right. The main reason for Sky Crane is it's in part to prevent the rockets from impinging on the ground and from puffing up dust and otherwise contaminating the rover. It's also because you just need a way to separate that jetpack from the rover no matter what. And it's hard to do that if the whole thing is actually sitting on the ground. It's actually much easier and safer to separate it when they're at some distance apart.
Did you stop it, Jason?
Yeah, I let her continue.
Okay.
So at this point, they're actually only headed to the ground at 3/4 of a meter per second. That's half a human walking speed, so it's very slow at this point that they're setting the thing down. And they're also setting it down vertically. No other Mars mission has ever come in vertically before. They've all come in at shallow angles. So it'll set it on the ground, and what happens at that point is as soon as the spacecraft or the jetpack detects that the load is off of those cables, pyros cut the cables and the thing flies away.
It just crashes somewhere.
It just crashes somewhere, and they don't show that part in the animation.
I wish they would. It will puff.
Yeah, it would look like a Wile E. Coyote puff, I think. I think it would be awesome. But
you can almost imagine that be the first target, right, is to go find its destroyed.
No, you would not want to do it. That's unexploded ordnance. That's like walking into a minefield. That is a really bad idea.
All right.
So, that it's certainly a complicated process, and there's more pyros being fired in this one than there have been for previous landings because there's a lot of steps.
I think they said there were 76 different pyrotechnic devices on there.
That's right. And so it's certainly complicated, but it's what's enabled them to land a mobile package this heavy on the surface of Mars. And the actual touchdown is going to happen at a very low speed. They have there's a lot of sort of leeway in that terminal descent part where they're descending at a fairly low speed, about 20 meters per second for most of the end of it. And that part, they're going to be pinging the ground the whole time. They're descending vertically. And so they can sort of use that. They call that the accordion part of the descent. They can just ride out. However, if they're too close at that point, they just go straight into the last part, or they can descend at 20 meters per second for a while. Once they detect that they've gotten within 21 meters of the ground, that's when they slow to that 3/4 of a meter per second descent. And it's really very slow and gentle by the time they touch down. I have seen some videos of them doing tests on the rover landing on some kind of scary surfaces, like a 30-degree slope with a rock underneath the middle uphill wheel. And it makes a clatter. It makes a huge racket when it contacts the ground, but it sticks. It sticks like Velcro. The thing does not slide anywhere. It's really incredibly stable. So they really have done their homework on making sure that they can deal with all of those kinds of contingencies.
Emily, is this that detector at the bottom of MSL right here, that little camera that you zoom into that says where it is and how far it is?
Yeah, that one is not actually, so that's not the radar part. That's an instrument called DIMES, Descent Imager for Mars something or other. I forget what that stands for. But the point of that camera is to provide context so that they can figure out exactly where the rover is within its landing site within hours of them touching down. In the past, it's usually taken longer than that. It's usually taken days because the images that we have of the surface are of too low resolution to be able to be perfectly confident. But now that we have high-rise data covering it, they're going to be able to match those DIMES images to the location of the lander fairly quickly. They are going to try to get high-rise images of the rover as soon as possible after it lands, but the orbit is not that favorable. So it might be a week before they get a good picture from orbit. Just because the MRO is not going to pass over the right spot on the surface of Mars to get a good photo.
And so if people want to plan their summer vacations to make sure that they get a chance to participate in the sort of festivities, when will everything start to happen?
Well, everything will start to happen. It all kind of unfolds very quickly on August 5th. The actual landing happens at 10:30 p.m. my time. So it's actually 1:30 a.m. Eastern time, and it's August 6th for most of the world. But for the place where the mission's being controlled from, it's August 5th. And it's really, these terminal events, they unfold in just the final hours before landing. So I do expect a ridiculous load on our servers at that time. We're going to be having a huge event called Planet Fest here in Pasadena. And there's also going to be satellite Planet Fests all over the world, and we're still looking for people who want to have basically house parties or parties at planetariums or whatever. It's
and we're going to probably do a Hangout to participate in it as well. So I think we'll be covering it on Google Plus at the same time and pitching in.
Yeah, and since the last landing, there's so many more tools for doing this kind of sharing that it's okay if our website goes down under the load, because I'll be tweeting, we'll have Hangouts, I'll probably do a landing Tumblr instead of putting it on my blog, because I do not expect our website to be able to survive the onslaught.
I highly recommend that you want to offload it over to Google Plus or YouTube or whatever you can. But yeah, no, definitely. And that was fantastic, by the way, Emily. That was such a great explanation of the landing sequence.
Well, thanks. And I should mention that I have one blog entry, a part of a 4-part series that I'm going to be doing, explaining all of this in excruciating detail. I'm posting the next step on Friday. That I realized I spent 2,000 words explaining what happens in 2 minutes on this mission. So it's there's a lot of things happening in a very short period of time.
And also, if people haven't seen it yet, there's a really great video that was produced by NASA covering the same thing and some interviews with some of the scientists. And it looks like it was done as a movie trailer, the music, and I don't know whether that bothered you or you thought that was awesome. I thought that was awesome. And in fact, it really felt like NASA did a really good job of getting across the excitement and the energy, and that this isn't some stuffy space agency, with some scientists. Like they're pushing the frontiers, and they've been able to build the production quality into their promotional material at the same time. I thought it was fantastic.
Yeah, and I think that they're actually doing a good job of using what they produce in a variety of different ways, because all of the animation parts of that video are part of the animation that Jason just showed, which is actually a very precise, exact demonstration of how all the parts work. And, of course, that animation is the one that I like because I'm a geek about that stuff. Yeah. But then they repurpose that material with the narration and the close-ups and stuff to produce a video that other people would like to share. So I think they're doing a really good job with that.
Yeah, absolutely. Kudos to the NASA team that worked on that. Whoever did the production of that did a fantastic job, and they should do all of that like that. It was great. Got a question for you. Lady Pembroke wants to know, are there still tickets for Planet Fest?
Yes, I have not heard that we're getting short on tickets.
Where do people get tickets?
Planetary.org/planetfest, or there's a link from our homepage, of course.
And how much do they cost?
I would have to look that up for you, but I will do it right now.
All right. And it's going to be, well, are you going to be in the neighborhood? You're going to be in the neighborhood, Ian, right? You're in LA. You going to go?
Yeah, because at the same time, the Mars Society convention's in Pasadena as well, and that's I think it's like from the 2nd to the 5th of August. So I'm going to be, hopefully I'm going to be emceeing the event again, because I tend to do that every year. Though on the 5th, I hope to be where the action is. So
that sounds great.
Yeah.
And Jason, I'm not sure where you're going to be. Online with us.
Not here.
No. I will be. Actually, August 5th, I'm going back East Coast by that time, so making a little move.
Cool. So if anyone has any questions, we can stick around for another couple of minutes. So if anybody has any questions for anyone on the team for any of the stories that we discussed, I should have mentioned this beforehand. We're happy to answer them. You can post a question either on the Google Plus chat, where this is being broadcast on Google Plus. You can post it on YouTube if you're watching us there, and you can also post it on your question onto Twitter with the hashtag #SpaceHangout, and we will spot it and be able to answer your question there. So Hannah Tankery asks, are there any videos of the tests they did on the landing MSL? I think the videos that you were talking about, Emily, watching it on different landing surfaces. Are those videos available somewhere?
I have not seen them. I saw those at the landing site selection meetings that they held for Mars Science Laboratory, so I have not seen those on the internet, no.
As a, I'm not your editor, but I think like an editor, and I think that would be a great blog post that you can get your hands on those videos and actually do a post on it. That'd be
the thing is, another thing that NASA is really careful about doing is not releasing content to just one person. If they're going to release it, it's going to be on their website for everybody to use. So you don't get exclusives like that.
Let's see. And I think that, by the way, I think that, if you're looking for a solution for how to showcase the videos, I think what Jason just did, that worked perfectly. Everyone was saying that looked great. So
okay, good.
So, Jason, what did you do to show that video off?
Basically, I just pulled it up on a separate window and then popped over here and screen shared it.
That's it?
Yeah. Okay.
Excellent.
Yeah, that worked great.
Planet Fest ticket prices about $30 a day for adults with discounts for members. Kids under 8 are free. Kids under 9 are free. Discounts for seniors and stuff as well. So ticket pricing is a little complicated, but you're not going to spend more than $60.
Sounds good. Well, I don't see any questions yet, so I'm going to give you one last kick at this, Ian, which is to talk a bit about some exoplanets.
Yeah.
You had another story that you wanted to talk about. So.
Yeah, in fact, because this week is a big week for exoplanet stories, particularly the atmospheres of exoplanets. And this one story that we published actually on Discovery News this morning, in fact, before I even woke up, which is kind of cool. But basically, Hubble is reporting that it managed to detect the atmosphere of an exoplanet, which is about 60 light years away. And the exoplanet is called a very memorable name, as always, HD 189733b. As I say, it's located like 60 light years away. And what happened was, when it was first discovered, I think it was back in 2010, I think it says, they didn't detect an atmosphere around it. It's supposed to be apparently it's a large, like a supersized Jupiter, and it orbits very, very close to its star, apparently 13 times closer than the planet Mercury orbits our sun. So it's basically a hot Jupiter. It orbits really, really close to its star. And they didn't detect an atmosphere. But then with the collaboration with, I think it was the Swift Observatory, the Swift Space Observatory, discovered that the star kicked off a massive flare. Now, this flare was an X-ray flare, so it basically pumped out a load of X-rays. And then almost immediately after this flare kicked off, Hubble analyzed the signature of the exoplanet orbiting the star and detected this huge plume of hydrogen generated around the planet. So then it suddenly discovered, oh, it's got an atmosphere. And of course, what the leading theory is that this flare basically hit this exoplanet and evaporated the upper layers of its atmosphere, so it could be observed by Hubble. And this is just a beautiful example of two space observatories working in tandem, able to detect an event that occurs on the surface of a star 60 light years away, and then analyze its impact, this solar flare impact, which apparently is way more powerful than anything our sun can produce. Like, it's something ridiculous, like 33 million times more power than the biggest X-ray flare our star can produce. But it basically then was able to analyze the atmosphere of an exoplanet again evaporated into space. I think that's a beautiful example of how these space observatories all work in tandem. So that was basically the big this morning, and I'm sure there's going to be more as the week goes on.
Well, that sounds fantastic. Have you seen that great graphic, what's on an XKCD, about all the exoplanets that have been discovered yet so far? And it was like all to scale and showing all the planets. I mean, 700 exoplanets now, I think, is the count. We're adding hundreds a month now, almost, it feels like. It's crazy how many exoplanets
I think it's actually approaching 800 now, isn't it?
Yeah, and just so many different kinds of planets, big ones, small ones. The fact they're detecting the atmospheres. We really are in the golden age of planetary. There it is. This is the one. Yeah.
Jason, you got it just seconds before I did.
Yeah, all 786 known planets to scale.
It's a beauty.
That's beautiful.
That's a fantastic. That's just and then there's our solar system, right in the middle there. That's where we are.
Right. We have discovered 768 planets, including the ones in our solar system. Yeah, that's fantastic. Great. Well, thanks again. So I mean, we've already pitched a bunch of stuff for the Planetary Society, but Emily, if people want to find out more about your work, where can they read you?
Planetary.org/blog.
Perfect. And Ian O'Neill in the great Discovery system, where can we find out more?
Yeah, you can see where I work at discoverynews.com, and I'm the space producer, so have a look on the space side, and there's lots of stuff, including the stuff from Jason. And yeah, it's you can find on there, and also a bit of news for astroengine.com. I've now decided to move the whole thing over to WordPress because I was fed up maintaining my own server. So hopefully you'll see more blogs on astroengine.com as well.
That sounds great. And Jason, where can we find out more about you?
I'm on lakesinthedark.com. I also write for Universe Today, and as Ian said, Discovery News Space, and you can follow me on Twitter at JPMajor.
That sounds great. And of course, you can find out more at my site at universetoday.com. The next thing we'll be doing is probably a virtual star party on Sunday night when it gets dark on the West Coast. So that'll be probably around 9 o'clock, and then we'll go until we've had enough. So that'll be on Sunday night, and we'll see everyone there if you want to watch it. So thanks again for watching our Weekly Space Hangout. Thanks to everybody who participated, and we'll see all of you next week.